So this is going to show how to use the Biot-Savart law to find the magnetic field around a long current carrying wire. This is done in the textbook. It's example 29.3. If you want to read along with the textbook to see where everything is coming from. So we consider a long wire. Of course, we can't draw it infinitely long, so we'll just draw a little bit long. Let's put an X and Y coordinate system on there. Put the X-axis through the center of the wire. The Y coordinate system goes up through the wire. There's our X and Y. And now let's write down our Biot-Savart law. So the magnetic field strength is the integral of mu naught over 4 pi times the current times ds cross r hat divided by r squared. So current carrying wire, of course, current I. So let's ask, what is ds cross r hat? The magnitude of a cross product. Yes, and if we're finding the magnitude of the magnetic field, we're using the magnitude of ds cross r hat. So let's ask, what is the magnitude of ds cross r hat? The magnitude of ds cross r hat equals the magnitude of ds times the magnitude of r hat times the sine of the angle between them. The magnitude of r hat is just 1 because it's a unit vector that points in the r direction. The magnitude of ds is just ds. So now let's get some of those things on the picture so we know everything we're talking about. ds is a little bit of length in that wire. It's pointing in the same direction as the current. So we'll say that ds points up. We'll say that the current flows up. So there's our ds. R is from our point in our wire to our point on the axis where we're trying to find the magnetic field. So there's r, which means that r hat is a unit vector that points in the same direction as r, and theta is the angle between ds and r hat. So there's everything defined. Let's put this in our integral. So now the magnitude of b is going to be the integral of mu naught over 4 pi times I times ds times sine theta over r squared. So there's all these things, and r, of course, is the length from here to our point. So now let's see, what else can we put in terms of x and y. So ds is a little bit in the y direction, which means that ds equals dy. Y is our distance from the y-axis to our point, so y is right here. X is from our wire to our point, so x is right here. Sine theta is opposite over hypotenuse, so sine theta is x over r. R is the hypotenuse of the right angle triangle, so r is the square root of x squared plus y squared. So there's all of our symbols. Let's put these things into our equation. So now the magnitude of our magnetic field is mu naught over 4 pi times I. For ds, we'll put in dy. For sine theta, we put in x over r, and then we have r squared on the bottom. So integral of mu naught 4 pi I x over r cubed, so r here gives us r squared, here gives us r cubed, times dy. Next we'll put in for r is x squared plus y squared to the 1/2. That's the same as saying it's to the square root of x squared plus y squared, which is the same as x squared plus y squared to the 1/2. So let's put that in. Square root is the integral of mu naught over 4 pi times I times x over x squared plus y squared to the 3/2. So the 1/2 comes from the square root, the 3 comes from the r cubed, times dy. There's our expression so far. So now we're doing an integral with respect to y. Let's ask, what are the limits of our integral? So we want to integrate over the length of the rod. This is a long rod, this is a long wire, so the limits go from minus infinity to plus infinity. So there's the limits of our wire. Now, as we do with all integrals, let's take our constants outside. So x is a constant, mu naught is constant, 4 and pi are constant, and I is constant. So the magnitude of our field is mu naught times I over 4 pi times the integral from minus infinity to plus infinity times dy over x squared plus y squared to the 3/2. So that's what we have so far. Now let's do a little math trick that's going to help us evaluate our integral. If we're going from minus infinity to plus infinity, that's the same as saying 2 times 0 to infinity. So we can write that down, times 2, 0 to infinity, and that's one of the properties of an integral, so long as it's symmetric on both sides. So now we've arranged for that limit a little bit. Next we can just look up the result for that integral, and that's one we're familiar with from electric field. So that gives us, so 2 on top here, 4 on bottom, that'll go to a 2 in the denominator, mu naught I over 2 pi. This integral, the result is y over x squared times the square root of x squared plus y squared. And that needs to be evaluated at infinity and 0. So to come on to our next page, to start evaluating our limits. So we've got, let's deal with the 0 first. Let's kind of deal with that guy. So we've got mu naught times I over 2 pi. Oh, let's see, we dropped an x way up here at the beginning. So if you notice that, good catch. So mu naught I and x were constant. So we have an x here, x here, x here. So we have mu naught I x over x squared. Of course, the one on top will cancel with one of the ones on the bottom, times. So that takes care of the x squared right here. Y over the square root of x squared plus y squared. And this one we're going to be evaluating as y goes to infinity. The other one's easier. What happens if y equals 0? The whole term is 0. So we have 0 over x squared, square root x squared plus 0 squared. That whole thing is gone. So now what we have to do to finish finding our magnitude of b is we have to ask what is the value of this as y goes to infinity, as y gets really big. So we'd like to be able to deal with this. The y in the numerator is kind of a problem because as y goes to infinity, this whole thing goes to infinity, even though there's a y squared on the bottom. So let's get the y out of the numerator by multiplying by 1 over y on top and bottom. So if we multiply by 1 over y top and bottom, that's going to become a 1 on top, and that's going to get easier to deal with. So we have mu naught times I times 2 pi times x outside of y times 1 over y is 1. And then we have 1 over y on the bottom. That would be the same as the square root of 1 over y squared times the square root of x squared plus y squared. And then we've got our plus 0 here, of course. Let's multiply our 1 over y squared inside. So that's x squared over y squared. So the 1 over y squared goes in. Y squared over y squared just gives us 1. So there's that term. Now remember, we were asking what happens here as y goes to infinity. As y goes to infinity, this whole term goes to 0. So we get 1 over the square root of 0 plus 1. That'll just give us 1 equals mu naught I over 2 pi times x is the magnitude of the magnetic field. So then the last thing we do is we don't restrict it to be horizontal. It's just a distance away from that rod. So it's just a distance here. Instead of calling that x, let's just call that r in general. So there's a distance r for a current carrying wire. We're asking what is the magnetic field right here. So the magnetic field right here is mu naught I over 2 pi r with a direction given by the right-hand rule. We know that makes big circles around the wire. We put our thumb with the direction of current and our fingers show the direction of the magnetic field. So there's our magnetic field around a long straight wire.